Hi, welcome back. So we're gonna start 4.3 here. In this section, we're gonna introduce the derivative of the exponential functions and then use calculus basically to analyze real life functions that involve exponential functions. So let's begin with the derivative of the exponential functions. Real quick, in the last section, we have reviewed the importance of the exponential functions in real life applications, especially in business calculus. In this section, we will extend these applications by analyzing the rate of change for these functions. Just when we, just as when we found the derivatives of other functions, we can actually also find the derivative of the exponential function by using the derivative limit definition. We've done this before in the in the second chapter, but we're not gonna do that for in this video. Instead, we're just gonna focus on the actual the derivative rule for the exponential function. So let's begin for this rule. For the purpose of this rule, let's assume that u is a function of x, and let's assume that u is also differentiable, right? So u is any function of x. And we define the exponential function as b to the x, right? Where b is any number, right? So this would be an example of an exponential function. Remind you that the base b needs to be greater than 0, cannot be a negative, and it cannot be 1. So there you go. So it has to be greater than 0, but not equal to 1. All right, so if I ask you, let's find the derivative of any exponential function, then the derivative of this will be itself, right? Itself. That's kind of neat, right? It's just itself, so it's not much of a change, right? Well, actually, what's going to happen is, right, we think about this as being copy and paste, right? You just copy and paste, right? You paste it here. But we also have to do another thing, right? We actually have to multiply by the natural log of b, right? So there you go, right? So there's a little catch in here. We have to do an extra thing to find the derivative. So it's not just copy and paste, but you have to do one more thing. Let's move on to the next example. And this example is when we actually have a function in the exponent, right? A function of x in the exponent. So this would be, for example, if we have 3 2x squared plus x plus 1, right? So if you notice, this is no longer just an x, but it's actual a function, right? So imagine that this is your u function of x. So when we do that, then we're going to consider this to be the inside part of the function. We're going to call this the inside of the function, right? I mean, it's an exponent, but it's the inside part of the function, and we're going to consider b be the outside, right? So what I'm trying to guide you here is to think about applying the chain rule, right? When we have inside versus outside, right? When we do the derivative of a function that have inside and outside, we have to do the chain rule. So let's do the derivative of the outside. The derivative of the outside, because it is an exponent, right, by nature. It's an exponent by nature. Then the derivative of an exponential function, we already said, is itself, right? So copy and paste. So derivative of the outside, it's itself. Keep the inside as it is, right? Keep the inside as it is. Like, remember that from chain rule. And then remember, because it's an exponential, you still gotta multiply by the natural log of b, right? So this pretty much just looks exactly as what we did before, right? But because this is chain rule, we have to multiply at the end by the derivative of the inside, right? So here we go. And that's pretty much it, right? So that's basically the derivative of the exponential function. As a consequence of this, we also have another rule that we can kind of define is an example or a specific example of the exponential function, and that is the natural exponential function. And remember that this looks like e to the x, where e is a specific value, right? E is in specific 2.71 something something something, right? So it's an example that's great. E is greater than 0 and not equal to 1, right? So it meets the definition. So when we take the derivative of this, it's going to be exactly as we did before, right? It's going to be copy and paste, right? And then we have to multiply by the natural log of e, right, of the base. But remember, what happens here is that these two are going to cancel each other out. In fact, you can put this in the calculator, right? If you have e natural log of e to the 1, this is equal to 1. It's equal to 1. So it's sort of like there's a 1 there always, right? It still follows this rule, but we know we're going to do this so many times that we say, oh, well, it's always going to be 1, so why write it out, right? Because it's always going to end up being equal to 1. So there's no reason for us to do that extra step because we're going to do that so many times. Then we just understand that it's just going to be copy and paste. No need to write this, right? Although it's there, we don't have to, again, because it's going to equal 1. So when you do that, the next example, when you say, okay, what's the derivative of e to the u, assuming that u is an example of, let's say, 3x squared plus 2x plus 1, right? Where this is a function of u, of x, right? So what we're going to do is exactly the same thing, right? We're going to apply the chain rule. I always assume that this is your inside and the exponential is the outside. So the derivative of the exponential is going to be e itself, right? Carry the inside, right? Leave the inside the same, like chain rule says. And then at the end, multiply by the derivative of the inside, right? So there you go, right? Of course, we're going to have a few examples where we're going to go over this, but I want you guys to think about it and have this rules handy, right? So these are adding to the table of all derivatives that we have to know.